let's take a look at stellar processes. And when I say that, what I really mean is we're going to look more at stars' births, stars' lives, and stars' deaths. And we'll start with more about star formation. So if you remember back to when we first talked about this, stars are formed out of nebulae. Nebulae are mostly hydrogen gas. They have a lot of mass, many times the mass of the sun. They have a very large volume, and the atoms within there are pretty far apart. But if a disturbance occurs, and this disturbance could be two nebulae colliding, or it could be a nearby supernova pushing a gas cloud and causing part of it to collapse. But whatever the cause, as it collapses, it becomes denser, it has less gravitational potential energy, and so therefore the gravitational potential energy is converted into kinetic energy of the molecules, which means that the gas cloud has a higher temperature. And if it continues to collapse, we'll get a denser, hotter center, and if it becomes dense enough and hot enough at the center, fusion can occur and we have a star. But for the cloud to collapse, the gravitational attraction has to overcome the motion of the molecules. Essentially, if we think about it in terms of energy, the gravitational potential energy of the cloud must overcome the kinetic energy of the gas molecules. And this leads us to something called the Jeans criterion for a cloud to collapse. The Jeans criterion for a collapse is that the absolute value of the gravitational potential energy of the cloud has to be bigger than the absolute value of the kinetic energy. In other words, the potential energy has to beat the kinetic energy of the cloud. And if we look at this, this tells us that cooler clouds, which have less kinetic energy, are more likely to collapse. Also, denser, more massive clouds are more likely to collapse because denser, more massive clouds have greater gravitational potential energy. Now let's look at fusion in stars. So we know that in main sequence stars, hydrogen is the fuel, but what exactly is the reaction that's going on inside of stars? Well, turns out that it depends on the star. For stars about the mass of our sun or smaller, in their cores, they undergo a series of reactions called the proton-proton chain. And the proton-proton chain looks like this. And I'm not going to narrate the whole thing, but do keep in mind that when I write down hydrogen 1, that's really just a proton. It's a proton by itself without any other objects within the nucleus. So with all of these reactions, what you notice is what goes in is hydrogen, and what comes out is helium with some extra hydrogens. So the net reaction is that 6 hydrogens went in, and we got out a helium nucleus plus 2 hydrogens, 2 positrons, 2 neutrinos, and 2 gamma rays. So 4 hydrogens are consumed in the process, and helium is spit out along with 2 positrons, 2 neutrinos, and 2 gamma rays. All right. The CNO cycle is what happens in the cores of stars that have about 4 times the mass of the sun. And this requires a temperature in the core greater than 20 million Kelvin. And I'm going to write down what happens in the CNO cycle. A lot of steps. There we go. And if you notice here, the net reaction is that 4 hydrogens go in, carbon-12 also goes in, and what comes out in the end is a helium-4, a carbon-12, 2 positrons, 2 neutrinos, and 3 gamma rays. So the fuel that was used up was hydrogen, and the ash, or the resulting stuff that comes out, is the helium, the positrons, the neutrinos, and the gamma rays. The carbon-12 went in, and the same thing came out. Now, the carbon-12 changed in the meanwhile. It became nitrogen and oxygen for a while. In the end, it turned back into carbon-12. Carbon-12 was like a catalyst for the reaction. Now, if you're wondering what happens in stars that are between about the mass of the sun and 4 solar masses, both the proton-proton chain and the CNO cycle are happening. Lower mass, there's more proton-proton chain. Higher mass, there's more CNO cycle. Now, no matter what type of hydrogen fusion is happening in the core, once the core uses up the hydrogen that's in there, the core doesn't have any more hydrogen fusion to support it. So it begins to shrink, and it heats, and then hydrogen fusion happens at a shell around the core, and then eventually, when enough helium builds up in the core, the temperature and pressure increase in the core until it can fuse helium in something called the triple alpha process. This requires temperatures of about 100 billion Kelvin. Here, 3 heliums combine to form a carbon-12. And then, if the star's mass is above 4 solar masses, then the core can become hot enough to fuse helium with carbon-12 to form oxygen. And it can continue by fusing oxygen with helium to form neon-20. And if the temperature gets to 500 million Kelvin, then it can even fuse 2 carbons together to form magnesium-24, or sodium-23 plus a hydrogen, or magnesium-23 plus a neutron. Or if the temperature can get all the way up to 1 billion Kelvin, it can fuse 2 oxygens together to form sulfur-32, or phosphorus-31 plus a hydrogen, or silicon-28 plus a helium, or sulfur-31 plus a neutron, and so on and so on and so on. The point is that in the cores of stars, progressively larger elements are formed through fusion. And this is called nucleosynthesis. It's the production of heavier nuclides by fusion in the cores of stars. And this is very important because this is how elements heavier than hydrogen are formed. The universe is primarily made out of hydrogen. The way that heavier elements are created is in the cores of stars. So nucleosynthesis is responsible for creating the carbon inside of you. It's responsible for creating the oxygen that we breathe now. It is responsible for creating the silicon that's in our computers, the copper that's in our wires, the iron that's in our blood. Everything heavier than hydrogen has been created in the cores of stars. Now, in massive stars, fusion can produce elements all the way up to iron and nickel, the most stable elements. But beyond iron and nickel, fusion doesn't release energy, so it can't support a star. So heavier elements than iron and nickel are not formed in the cores of stars, at least not through the process we've looked at. So how do we get these heavier elements? Well, there's 2 methods. Method 1 is the S process, for slow neutron capture. So if you note above, some of the reactions produced neutrons. In cores of stars where neutrons are produced through fusion reactions, neutrons can approach other nuclei and come close to them because there's no electrostatic repulsion. If the neutron can get close enough to another nucleus, the nucleus can capture that neutron through the strong force. If this happens, then we can get a nuclear reaction like the following. So say we have an element here, and it captures a neutron. That will form an unstable isotope of that nuclide. Then, that nuclide can undergo beta decay. It'll emit an electron and an antineutrino, and then we get a new element with 1 more proton than the original element. This method is a way of producing elements all the way up to bismuth-209. Past bismuth-209, it doesn't really work. So that's the first way that we can get heavier elements. The second method is called the R process, which stands for rapid neutron capture. So if you remember back to supernova, in a supernova we get this reaction where protons and electrons can combine to form neutrons and neutrinos. So this produces a huge number of neutrons and neutrinos, and it produces them very, very quickly. So in this situation, where there's a huge neutron flux, a huge flow of neutrons in the star, the neutrons get added to nuclei faster than those nuclei can decay by beta-minus decay. Essentially, just neutrons just keep getting added to nuclei during supernovae. So what we get is very heavy nuclei are formed with many, many, many neutrons. But there are also a lot of neutrinos. So this strange reaction can happen where a neutrino and a neutron can combine inside of a nucleus to form a proton and an electron, and the electron escapes. So very suddenly, in these supernovae, very heavy nuclei of all sorts are formed by rapidly capturing neutrons. And everything heavier than bismuth-209 is created in this way, and that includes radon, uranium, and other elements. Now for a moment, let's go back to the main sequence, and let's talk about the lifetimes of stars while they're on the main sequence. So remember that the luminosity of a star is proportional to its mass to the 3.5 power. So if a star has a mass 10 times greater than the sun, its luminosity is 10 to the 3.5 times greater than the sun, or 3,200 times greater than the luminosity of the sun. Okay, so 10 times the mass means 3,200 times the luminosity. That means 3,200 times as much hydrogen fusion is occurring every second in the more massive star. So, yeah, it's 10 times more massive, but it's using up the hydrogen 3,200 times more quickly. It runs out of hydrogen more quickly. More massive stars have shorter lifetimes on the main sequence. And let's see if we can estimate how much shorter. So luminosity is equal to energy per time, or energy emitted per time. So let's say a star burns some fraction of its mass while it's on the main sequence, and we'll call that fraction this letter kappa. Then we can write luminosity is equal to kappa mc squared over the lifetime of the star. And the mc squared comes from E equals mc squared, because the portion of the star that gets fused, that's what's turned into the energy. So if we use that, okay, we can rearrange this and get that the lifetime of the star is equal to kappa mc squared over the luminosity. And we know that the luminosity is proportional to m to the 3.5 power. So we can set up a proportion, kappa mc squared over m to the 3.5. So the lifetime of the star is proportional to kappa c squared m to the minus 2.5. The lifetime of a star is proportional to mass to the minus 2.5 power. So if a star has 10 times the mass of the sun, then we'd expect its lifetime to be 10 to the minus 2.5 times the lifetime of the sun. And if we do that, then the lifetime of a star with 10 times more mass, it's 3.2 times 10 to the minus 3 times the lifetime of the sun. Well, the lifetime of the sun on the main sequence is about 10 billion years. So a star with 10 times the mass would have a lifetime of about 32 million years. And that is how we can estimate the lifetime of a star on the main sequence. And now let's look at supernovae. And we're going to look at two different types, type 1a and type 2. Type 1a are when a white dwarf and a binary collapses, and type 2 is the classic exploding star which produces a neutron star or a black hole. Let's look at type 1a first. So a type 1a supernova requires a binary system, where one star has evolved off of the main sequence and become a white dwarf, and the other one becomes a red giant. The red giant has to become big enough that some of its mass falls or accretes onto the white dwarf. So we have a red giant here, a white dwarf here. The red giant has become big enough, has swollen large enough that some of its mass is actually falling onto the white dwarf. So the white dwarf's mass increases as it gobbles up some of the red giant. Now recall, there is a limit to the size of a white dwarf. That's the Chandrasekhar limit. There is a maximum mass that a white dwarf can have. That's about 1.4 solar masses. Above this, the electron degeneracy that's holding up the white dwarf can't provide enough outward force to support the star. So in a type 1a supernova, the white dwarf mass exceeds the Chandrasekhar limit. The white dwarf collapses very suddenly, and all of the carbon in the white dwarf fuses very, very quickly in a massive explosion. There's a huge release of energy in this as the carbon fuses suddenly. The star explodes completely, leaving no remnant behind. Now, this explosion, it always occurs when the white dwarf mass is at the Chandrasekhar limit. So it's usually a very uniform type explosion with the same luminosity. If it has the same luminosity, and we know that luminosity, we can measure the brightness from Earth, and if we know the brightness and the luminosity, we can get the distance. Now, the luminosity of a type 1a supernova is about 10 to the 10 times the luminosity of the sun. 10 billion times greater than the luminosity of the sun. That's like the light from an entire galaxy coming from one star. These are very useful when we're looking over very large distances. The type 1a supernova can be used as what's called a standard candle. A standard candle is an object of known luminosity, which can then be used to get the distance. And other standard candles that we've encountered are Cepheids. They're objects where we can determine the luminosity, and then if we measure the brightness from Earth, we can get the distance. Now, type 2 supernovae is when very heavy stars fuse heavier and heavier elements in the core. And we've seen this a couple times before, but remember, eventually iron and nickel are created at the core of the star, and fusion of these elements does not release energy, so the core collapses. There's no more outward pressure from fusion, so gravity wins, the core collapses. If the core cannot be held up by electron degeneracy, as in very heavy stars, the protons and electrons fuse to produce neutrons and neutrinos, so there's a huge neutron flux, and that's where the R process comes in. And if neutron degeneracy is able to hold up the core of the star, the falling material, where the core used to be, the outside part of the star is now falling inward, it suddenly stops as it hits that dense core, this neutron star that's formed, and an outward shock wave is produced, which moves outward, causing an enormous explosion. The outer part of the star completely explodes. These tend to be slightly lower luminosity than type 1a supernovae, and they can be distinguished from type 1a supernovae by their spectra and how the luminosity varies after the explosion. The type 1a is a more consistent decrease, while the type 2 has kind of a big sharp peak, a sudden decrease, and then a kind of a plateau like that. So the luminosity can be observed over time, and we can determine what type of supernova we're looking at.